Hello, my name is Dan Cziczo, and I'm a professor at Purdue University in the Department of Earth, Atmospheric, and Planetary Sciences. I'm here today to talk about tipping points in atmospheric science with an emphasis on climate change for science for the public. So let's go ahead and get started and talk about this very, very interesting and very timely topic. So any understanding of climate in the Earth system really has to begin with a temperature record of the planet. And we're able to acquire these through a number of different proxies. Proxies can be anything from ice cores to tree ring data to fossils that we know are sensitive to climate. And using those sources, we're able to look back in time at the Earth. And this plot is one such proxy record using a number of different proxies. And using it, we're able to look back over almost 1 million years, 800,000 years in this case. And the first thing that you'll notice is it's not an absolute temperature. It's not degrees C or degrees Fahrenheit. These types of records are usually anomalies, meaning differences from a certain temperature. And that certain temperature can be a global average in a certain year. The year might be 1900, 1950, year 2000. And so looking back in time, we can see that there's different periods of time that are a good bit colder than it is now, and these are commonly called ice ages. And there's periods of time that are similar to the temperature now, and these are called interstitial periods. And I think everybody that's watching this should be very happy to know that we are currently living in an interstitial period, not in one of the ice ages that many of us have probably read so much about. One thing that's commonly looked at is that that temperature record has something like a heartbeat. There's interstitial periods, and then there's periods in an ice age, and then another interstitial, and they look like they have a repetitive pattern. And this was something that was picked out almost 100 years ago now by scientist Milankovitch. And these are called Milankovitch cycles. And what Milankovitch understood was that a lot of these periods could be attributed to orbital mechanics. How the Earth's eccentricity around the sun changed, how the Earth precessed like a top differently at some periods versus other periods, or if the Earth was tilted a little bit more towards or a little bit more away from the sun. And summing these up, we commonly term these now to be Milankovitch cycles. And they explain most of what we see of the climate of the Earth, especially dating back over long periods of time, these hundreds of thousands of years. In fact, Milankovitch really worked out the physics of this, was able to look at these different variables, the tilt, the eccentricity, that type of thing, the precession of the Earth, add them all together and come up with something that we would term daily insolation, the amount of sunlight reaching the surface of the Earth. So that insolation, the amount of sunlight, was really the summation of all of these different orbital parameters of the Earth. And they could be matched up very nicely with those fossil records, those ice core records, those proxies, and give us an understanding of what the Earth's temperature was going back into the past, explaining that heartbeat, that periodicity, and also look at what the Earth's temperature should look moving into the future. So what we can do is zoom in on that temperature record somewhat. Instead of looking at 800,000 years, let's just look at the last few thousand years, sort of the most recent recorded history of the planet. And over those few thousand years, those orbital parameters are not expected to change very much. And so you might think that otherwise the temperature of the planet would be a flat line. And speaking of the changes, that temperature anomaly that in the last figures was plus or minus 4 or even 8 degrees centigrade, you can see now that over the last few thousand years, the temperature anomaly of the planet has been very small, a few tenths of a degree. You'll notice that there's two colors on here. There's sort of a light green color, and that has to do with these proxy records, these ice cores, tree rings, fossil records, that type of thing. And then there's a blue part of this plot. And the blue denotes the time period that scientists feel that we've had accurate thermometers. And that's only really been since the year 1880 or so. There's a few locations on the planet that had accurate temperatures before that, but it wasn't until the 1880s that we had a sufficient amount of high quality temperature records. In the United States, for example, the acknowledged oldest record of time is from Massachusetts and really dates only back to the late 1800s. So a few things become obvious when we look at this. There are some small scale features on here. Warmer and colder periods. Warmer periods like the medieval warm period. Colder periods often attributed to things like volcanoes. Volcanoes throw a lot of particulate matter into the atmosphere, something that we'll talk about more later in this video. What's quite striking, though, is that this record as a whole is very flat. It's very stable. There's no major temperature shifts. And so one of the take-home messages here is that human civilization has really evolved in an incredibly stable climate. We don't see these 4 or 8 degree temperature swings. Everything has happened within a few tenths of a degree. We have adapted to our climate, and the climate has been very stable, allowing us to adapt over long periods of time. Something that should be quite striking about this is that if there is a temperature anomaly, it's only happened within the most recent few decades, since we've had this very high quality temperature record using thermometers. And this, of course, is climate change, global warming, what we'll talk about more. That temperature rise can't be explained by the Milankovitch cycles. It's not due to the orbit of the Earth. It's not due to something like a change in the output of the sun's energy, this solar insolation. So we have to ask ourselves, what are the other things that can affect Earth's temperature? And we've actually known about the things that can affect Earth's temperature other than those orbital mechanics for even over 100 years, longer than Milankovitch. And these really date back to folks like John Tyndall and another scientist, Eunice Foote. Tyndall and Foote did a number of different experiments looking at different gases that could impact temperature. And so we'll slow down here and try to explain this for a few moments. What Tyndall did was built an instrument. He called it a comparative spectrometer. It was basically a very fancy tube that he was able to fill with different gases. And then he was able to pass different types of light through that tube. These lights might be visible, the types of things that we're seeing with. They could be ultraviolet, they could be infrared. Infrared really being heat, like the heat that the Earth picks up after it becomes warm. And what Tyndall and Foote found was that most of these gases that they looked at were essentially inert. They didn't interact with that radiation. They didn't interact with that light almost at all. They just let the light pass through. What they did find was that there were a number of different gases. Very small quantities of these are found in the Earth's atmosphere. Things like CO2, ozone, nitrous oxide, methane, water vapor, that were able to absorb infrared energy, the heat that was being given off by the planet. They were able to absorb it and then re-emit it. So why is this important? Well, the idea is that even though you have these very trace amounts of gases, like CO2 in the atmosphere, once the planet warms up, and gives off heat, gives off infrared energy, that CO2 in the atmosphere can reabsorb that energy. Half of it is transmitted upwards, presumably back into space, but half of it is transmitted back downwards. And so it can act like a blanket. If we get cold on a winter night, we throw an extra blanket on. The blanket isn't producing heat. What it's doing is it's trapping heat and re-radiating it towards our body, thereby keeping us warm. This is often termed the greenhouse effect, and the idea is that these trace gases, the ones that I mentioned earlier, even though they're of low abundance, are very important to the planet because they're able to trap some of the heat that would otherwise escape to space. So we can imagine that there was a CO2 cycle, a greenhouse gas cycle, before humans were even involved in the planet. There was CO2 here, and it participated in the Earth's climate. That CO2 was put out by a variety of different sources, but one of the big ones is volcanoes. So you can imagine a volcano on the right-hand side of this figure pumping out CO2. And that didn't just build up in the atmosphere. CO2 didn't start from some low level and get much, much higher. It was stabilized by something. And it turns out that it was often wrapped up in sediments and then buried and taken out of the system. And so this happened over millions of years, and this time scale is going to become important because, of course, we're seeing this large rise in temperature, which is attributed to greenhouse gases, but it's happening over decades. The Earth has something of a thermostat. It's built a regulatory system, but it doesn't operate on the yearly basis. It operates over millions of years. So before humans, how would this work? you'd increase CO2, presumably by volcanoes, although there are some other sources. That would increase the amount of CO2 in the atmosphere. You would have a cycle where silicates rocks weathered that allowed for the burial of sediments, in this case calcium carbonate containing some of that carbon. That would lower the CO2 in the atmosphere, and you would be able to stabilize CO2 at some level, thereby leading to a relatively stable climate. You can ask yourself some questions about what would have happened if some part of this mechanism worked too well and some other part didn't work as well, that they didn't balance out. And so the easy thing to imagine here is that perhaps you would have more or less volcanic activity. So let's think about less volcanic activity for a moment. Say that there was a period of time that less volcanoes erupted, less CO2 was being put into the atmosphere. But your removal system, the silicate weathering leading to sediments that were then buried and removed, would still be pulling CO2 out of the atmosphere. You could get to very low CO2 levels. It'd be like taking that blanket off on a winter night. And in fact, this did happen, that we went into some super ice ages in the Earth's history in the past. These have often been referred to as snowball Earth events, where the planet had so little CO2, became so cold, probably also as a consequence of some of those orbital mechanics being a bit further away from the sun or having a higher eccentricity or just the right tilt, that it led to the Earth becoming very cold and essentially almost ice covered. And so this is not an image that we have. These would have happened many millions, billions of years ago. But this is an image of what the Earth probably looked like, with very little open landmass or little open water on the surface and otherwise ice or snow covered. You can ask yourself, well, how would we have gotten out of this? Well, over time, there would have been increased volcanic activity. CO2 would have built up in the atmosphere, and eventually it would be like putting more and more and more blankets onto somebody during the wintertime. And eventually you're able to break out of this snowball Earth, or this frozen Earth period. And that's exactly what happened, probably on at least 2 occasions in the Earth's past. Again, this is completely natural, completely normal cycles of climate in the Earth's history. But we can also ask what's going on now that we're in a period where humans are involved in the climate equation. And it turns out that, again, on a yearly basis, there's a very natural climate cycle where plants conduct photosynthesis, they respire, and so on. It turns out that that would go on with or without humans. But humans have perturbed the equation, predominantly through the burning of fossil fuels, also through some agricultural practices that make for some of those other greenhouse gases. But we can think of the predominant one as being the burning of fossil fuels, taking fossil carbon, carbon that was captured and held in the Earth system, burning it and emitting it as CO2 into the atmosphere. So instead of just having these volcanoes maybe pumping out CO2 via eruptions, now we have this constant source, this new source of carbon going to the atmosphere because of human activities. And this is going to perturb the system in a very interesting way. So we can look at something like a time record of CO2, and this is shown in parts per million, molecules per million in the Earth's atmosphere, versus year. You can see that this record goes back to something like the 1950s. And this is when some of the first records of CO2 in the atmosphere, the first long-term record, this one made at Mauna Loa in Hawaii, was starting to be conducted. And so we've been able to measure that CO2. And instead of seeing this sort of annual cycle up and down because of plant matter, you see that annual cycle, that periodicity over the year, but you also see a constant increase in CO2. And that constant increase is because of the burning of fossil fuels. This is the human contribution to the CO2 equation. And so there's a quote from a recent report from the Intergovernmental Panel on Climate Change that atmospheric concentrations of carbon dioxide and the other greenhouse gases, methane, nitrous oxide, are due to human activities, or at least in part due to human activities, have increased to levels unprecedented in at least the last 800,000 years, that long-term climate record that we showed at the beginning of this talk. Carbon dioxide concentrations have increased by 40% since pre-industrial times, and this is having an impact on the temperature of the planet. So What does this mean to climate? This is also a topic that had been considered for a number of years, actually dating back to at least the early 1900s, late 1800s. And one of the leading scientists was Svante Arrhenius. So Arrhenius has a few very seminal papers on this topic, and this is one of his quotes. If the quantity of carbonic acid, CO2, increases in geometric progression, the augmentation of the temperature will increase nearly in arithmetic progression. Essentially what Svante is saying is that if we increase the amount of CO2 in the atmosphere because of human activities, the temperature of the planet will go up. Arrhenius is one of the first folks, really the first person that was attributed to thinking about this idea of climate sensitivity. If we increase CO2 because of human activities, how much does temperature rise? He first considered this in the late 1800s, 1896, and came up with a figure that if we doubled the amount of CO2, based upon the lab work of folks like Foote and Tyndall, that the temperature of the planet would increase by about 5.5 degrees centigrade. He found a math error in his paper. He later revised that downward to about 4 degrees, so not quite the sensitivity that we thought that was there. He wasn't actually looking at this for the reason that we might think. Svante was actually from Scandinavia, and so he was thinking that the planet was actually too cold for Scandinavia, and was thinking about the idea of increasing the CO2 of the planet, essentially changing the CO2 concentration to warm the planet up. He was trying to get some idea of how much CO2 had to be emitted to get a change that he was interested in. There's a common term called geoengineering now, the intentional changing of a planet's climate. And in some ways we can think of Svante as being one of the early geoengineers trying to actually warm the planet up, not foreseeing the increase of CO2 due to human activities, which has already done much of what he was considering in the late 1900s. So we showed that figure from the Intergovernmental Panel on Climate Change report that there's been an increase in CO2 and the attribution that there's been an increase in other greenhouse gases as well. And so that's absolutely true. So then we can ask ourselves, what have we seen as an increase in the planet's temperature? So since 1880, this year that scientists generally agree we had enough high quality thermometers, we've seen the temperature of the planet warm. The figure here is since 1900. We have data going back to the 1880s. Globally average, the temperature of the planet is now greater than 1 degree C warmer, close to 1.5 degrees over land, actually slightly more in recent years than it was in 1880. CO2 has gone from 280 parts per million to 400, this increase of more than 40%. We can also think about warmest years on record. And so right now we're in the middle of 2020. The warmest year on record is 2016. Last year, 2019, was second on this list. And you can see that all of these years have occurred since the year 2000, the top 10. 2020, where we sit right now, is tracking to be either number 1 or number 2. So a year like 2009 is going to get pushed out of the top 10, and we're going to slide in 2020. So it continues to warm and continues to get warmer, tracking that abundance of CO2 in the atmosphere, which is completely in keeping with the science that has been done since the mid to late 1800s. So none of this is new, none of this is unexpected at this point. There is a bit of new science. There is some stuff that we're only now starting to really understand. And one of those things is the attribution or the expectation of what particles do in the Earth system. So the image that was just X'd out is an image, a mosaic of the Earth produced by the Japanese Space Agency, and intentionally edited out were things like dust storms, clouds, storm systems, forest fires, that type of thing, to give you this beautiful image of the Earth. At any one time, the Earth actually looks more like this Apollo image, where you can see all of these things present in the atmosphere. You can't see some of the surface of the planet because there's clouds in the way. Those clouds are rather bright, they're rather white, and so what you can imagine is that there's being sunlight reflected back into space by the presence of those clouds. So it's known that humans are changing particulate matter in the atmosphere. This is having an impact on climate just like CO2 is. It's offsetting some of the global warming attributed to the greenhouse gases, offsetting, but it's not at the same level or greater. The Earth is not becoming cooler as a result of particles. We're just not as warm as we would be if it was only for the increase in greenhouse gases. So this sometimes is difficult to understand, but I think a picture like this gives us an illustration of what's going on. So this is the city of Singapore. This is during a period where there's been a lot of intentional biomass burning for clearing of land. And so this human-made smoke pall is existing over the city. This would otherwise be a bright, sunny blue day, but what's happening now is that sunlight is striking these particles, and from the observer, from the camera, you can see this very diffuse radiation, some of it being reflected back out into space. So let me repeat this. This is energy from the sun that would otherwise strike the surface of the planet and warm it up, that's being reflected back into space because of human activities. So again, a cooling effect that's counteracting, but not balancing out, some of the global warming due to the greenhouse gases. This is often called the direct effect of particles. There's also an indirect effect of particles, that these same particles you're seeing here can form the seeds, or act as the seeds on which water droplets or ice crystals, clouds form. So there's an indirect effect of particles forming more of those very bright white clouds that we saw in that Apollo image earlier. Again, offsetting some amount of greenhouse gas warming. So we can think of an accounting of all of these things, and that's what's shown here. So this is again from the Intergovernmental Panel on Climate Change. You can see that there's an observed warming. How much do we know that the planet's warmed? We can then think about the warming due to greenhouse gases, large positive contribution. Other anthropogenic forcing, in this case these particles as well as the clouds that they form, have a negative. You can see that the negative is not of the same magnitude as the positive. So when you add these things up, you still have global warming, but not as much as you would have had just from the greenhouse gases. The combined forcing that we know of is very similar to the observed warming, meaning that we're doing our accounting properly. We also know, looking back at Milankovitch, looking back at solar output, that the natural forcings in the system and other changes in the Earth system have not accounted for this warming that we've seen. It's not true that the sun's energy is somehow leading to a warmer planet. The sun has not changed in intensity by enough to explain that. And so what we're left with is a warming and a continued warming of the planet as we burn fossil fuels. So it's pretty natural at this point to ask ourselves, is there something that we can do about this? This is not a new question. So this is a report that came out in 1965. So this would be the Johnson administration. So this is over 50 years ago. And the quote is here for you to read, but there's clearly an understanding over 50 years ago that CO2 increases in the atmosphere was going to increase the temperature of the planet. They were acknowledging that global warming was and would continue to occur and actually increase. And they're asking a question, is there something that we can do about it to change the temperature of the planet back? So this report has a number of ideas in it, some of them realistic, some of them unrealistic. But what we've come up with in the modern day is that there are a couple paths forward to removing that CO2 from the atmosphere. And again, you can imagine that even in the modern day, some of them are realistic, some of them have side effects, and we'll talk about those in the next few slides. The first and probably the most obvious thing when faced with an increase in carbon dioxide in the atmosphere is to do what the natural system does, which is find a way to remove that CO2, remove the warming agent from the planet's atmosphere. This is commonly called carbon sequestration. This is an overview page from a National Academy's report on the topic from a few years ago. And just to make sure that the viewer doesn't think that this is science fiction, this type of work is actually already going on. There are things like oil and natural gas drilling projects that remove things like natural gas from subterranean reservoirs. When they pull that out, it has natural gas, but there's a high amount of CO2 with it as well. And so what is done is that CO2 can be separated out and then re-injected back into whatever reservoir there is for that natural gas. It actually increases the amount of material that can be pumped out by keeping the pressure very high, but it also has the side benefit of re-injecting CO2, which otherwise would be just released into the atmosphere, thereby increasing global warming problems. So it's got a double benefit in this case. Carbon sequestration in general is not meant to increase the productivity of something like an oil or gas well, but the idea is there that you get this double benefit. The prime thought here, though, is that you find a way to capture that CO2, whether it be at the stack or from the atmosphere, and then force it back into the Earth system. This is just one idea for sequestration. There's a number of other ideas, including increasing plant growth, that type of thing, that would lead to the same result as long as you take that material and find a way to sequester it, to bury it, take it out of the Earth system so it couldn't be then re-emitted. There's a second report on this topic, and this is a catchphrase often called geoengineering. So we mentioned this when we were talking about Svante Arrhenius and his wish to increase the temperature of the planet because he was living in Scandinavia. In the modern day, geoengineering, this idea that we can somehow manage the climate of our planet, often is attributed to the thought of changing something to reduce the temperature, but not the idea of sequestering carbon, doing something else, another countervailing technology. And I just want to be very clear about this. The idea is to return the temperature of the planet to a lower level, but not remove the CO2. And so what you're doing is you're masking an effect. And so you can imagine that there's a number of side effects depending on what strategy you use here. One of the predominant strategies that's used is this idea that particles mask some sunlight from making it to the planet. They don't allow all of that sunlight, much like that earlier figure that we showed. And so it's been discussed to increase the particulate loading of the lower part of the atmosphere, the troposphere, the part we live in. So that would be one attempt, or increase the amount of clouds in the troposphere. Again, like that image that we saw earlier from Apollo, increasing the number of those white bright surfaces. A secondary idea would be to put those particles higher up in the atmosphere, in the stratosphere, where they're more stable. This is very often where particles from things like volcanoes go. And you saw those figures earlier with the temperature record, where there were cooler periods in Earth's climate due to volcanic emissions. And so these are often thought of as being natural examples of geoengineering. But that analogy only goes so far, because a volcano is a transient. It puts particulate up, but then it will eventually fall down. Same thing with particles or clouds in the lower atmosphere. Particles can be put there by something like a forest fire, but they'll eventually settle out of the system. When we think of geoengineering strategies, it is actually completely different, because you have to acknowledge that those particles have to be kept there at some level. You have to keep injecting them. As soon as they fall out, you have to put more in. So it's no longer a transient, it's now a constant. And it's not even constant, it has to increase in some way so as to offset the increasing amount of greenhouse gases. Because you're acknowledging that you're not actually trying to stop the problem, you're not trying to stop the CO2 emission. And so there's some downsides to this. One of them is probably pretty obvious from looking at that diffuse sunlight in the picture of Singapore that we showed earlier. One of the consequences of this, when we think back to that image that we showed earlier of the diffuse light over Singapore due to the abundance of small particles in the atmosphere, is the impact that we have on solar energy production. When we put a lot of particles into an atmosphere and we start reflecting sunlight, start diffusing sunlight, we have an impact then on solar energy production, solar cells, or especially direct beam generation of power from sunlight. And so a consequence of trying to reduce temperature by putting particles into the atmosphere is that you actually break down one of the mechanisms, one of the things that you're trying to generate energy from, solar energy production. So you're more reliant in this case on energy production by fossil fuels. You thereby perhaps increase the combustion of fossil fuels and offset some of the good that you're trying to do by dropping the temperature. Another issue that we have is that we mentioned earlier that these small particles act as the seeds on which droplets and ice crystals form. They act as the seeds that clouds form on. And what we know is that clouds end up producing precipitation. They're an important part of the water cycle. So what's the consequence of this is that we change precipitation patterns. And this can change depending on where you put those particles, if they're in the troposphere, if we're trying to change clouds, or if we put those particles, if we try to mimic one of these volcanic eruptions and put them in the stratosphere. So the images that we're seeing now are for changes in precipitation based on putting particles in the stratosphere, the next layer of the atmosphere up. They fall out and they affect cloud formation. So a consequence of this is that you could increase precipitation in some locations, thereby perhaps increasing flooding. You can also decrease precipitation in certain locations, thereby inducing a drought. Another thing that we know from volcanic eruptions where we put particles, or where particles are put into the stratosphere, is that those particles act as sites that lead to the loss of ozone, reactions that lead to ozone destruction. And the ozone layer is an incredibly important part of our atmosphere. It's something that filters out dangerous ultraviolet radiation, the type of radiation from the sun that can actually do things like cause skin cancer. So if we start putting these particles into the stratosphere, we have a very high probability of reducing ozone and increasing skin cancer as a consequence of, again, this attempt to drop the temperature of the planet. So we'll just close with an ethical thought here, and this is something that I can't answer for the viewers of this. I think everybody is going to have to answer it for themselves. But we have to ask this question: when do you stop doing research in an area, or when do you stop thinking of this as a potential solution to climate change? Is there something that you're not willing to do? And so for me personally, I'm not willing to think about reduction of the ozone layer and possible increases of skin cancer in an attempt to drop temperature. I believe that the better idea is to try to sequester carbon, to try to capture that carbon and find a place to store it, as opposed to masking the effect with something like particles being put into the atmosphere or trying to change cloud cover. But again, this is a question that everybody here is going to have to answer for themselves as we move forward into these unknown areas of research. So we'll just close by presenting this figure on the increasing temperature of our planet. And again, this is over the last few decades. This is not something that's due to changes in orbital mechanics or increases in the output of the sun. These are changes due to increase in CO2 and other greenhouse gases due to human activities. And we can see that this is not only an increasing positive temperature, but the rate of increase is also going up. So we're getting warmer, and we're getting warmer faster. And so this is something that we are going to have to address as a civilization, especially as we move out of a range that our civilization has really adapted to in the past, and start asking ourselves if this is something that we're going to need to address more quickly with some of these ideas like carbon sequestration, or if it's something that we can address by changing our usage of energies. I'd like to close with that and say thank you for your time.